The inspiration for devices that provide invisibility and next-generation technology has been derived from an insect found in the backyard. Greetings, everyone! Today we will be delving into the fascinating world of synthetic brochosomes, a breakthrough achieved by the brilliant minds at Penn State University. These artificial replicas mimic the structure of the minuscule particles found on the wings of leafhopper insects. The implications of this innovation are far-reaching, as it opens up possibilities for the development of cloaking devices and more efficient solar energy harvesting systems. These brochosomes possess a distinctive shape reminiscent of a soccer ball, complete with cavities that remarkably decrease light reflection by an impressive 94%. What's truly remarkable is that the researchers discovered that the size of these cavities remains consistent across various species of leafhoppers. This consistency allows for the absorption of ultraviolet light, effectively rendering these creatures invisible to predators with UV vision, such as birds and reptiles. Additionally, the scattering of visible light provides them with an anti-reflective shield against potential threats. Without further delay, let us dive into our captivating discussion. According to Tak-Sing Wong, a professor of mechanical engineering and biomedical engineering, this breakthrough has the potential to facilitate the creation of optical materials inspired by nature. These materials could have a wide range of applications, including, but not limited to, invisible cloaking devices and more efficient solar energy harvesting coatings. Wong spearheaded the research, which was recently published in the Proceedings of the National Academy of Sciences of the United States of America, PNAS. Scientists have been puzzled by the purpose of the distinctive, minuscule particles with a peculiar soccer ball-shaped structure and empty spaces, which have been observed in insects since the 1950s. In 2017, Wong and his team at Penn State University took the initiative to generate a rudimentary artificial replica of brochosomes in order to gain a deeper comprehension of their role. Lead author of the study, Lin Wang, a postdoctoral scholar in mechanical engineering, expressed the potential significance of this finding for technological advancement. Wang stated that by implementing a fresh approach to controlling the reflection of light on surfaces, it may be feasible to conceal the thermal signals emitted by humans or machines. The possibility of creating a thermal invisibility cloak inspired by the mechanisms employed by leafhoppers is not out of reach. This research demonstrates the value of studying nature in order to drive the development of contemporary technologies. Despite scientists having knowledge of brochosome particles for over 75 years, Wang explained that their production in a laboratory has proven to be challenging due to the intricate geometry of the particles. The reason behind the leafhopper's production of intricately structured particles has remained elusive, explained Wang. Through the utilization of advanced 3D printing techniques, we successfully replicated these brochosomes in the laboratory. Our findings revealed that these artificially created particles have the remarkable ability to diminish light reflection by an impressive 94%. This groundbreaking revelation is significant as it unveils a previously unseen phenomenon in nature, where hollow particles are employed to precisely manipulate light. There have been various theories surrounding the purpose behind leafhoppers adorning themselves with a protective layer of brochosomes armor. Some have suggested that it serves to shield them from pollutants and moisture, while others have likened it to a superhero's invisibility cloak. However, a recent revelation regarding their unique geometry has shed light on a compelling hypothesis. The primary function of this armor may actually be to provide a cloak-like camouflage, enabling leafhoppers to evade potential predators. This insight comes from Tak-Sing Wong, a distinguished professor of mechanical engineering and biomedical engineering who serves as the corresponding author of the study. The significance of the holes in the brochosomes, which contribute to its spherical resemblance to a soccer ball, has been discovered by the researchers. Remarkably, the size of these holes remains constant across various species of leafhoppers, regardless of the size of the insect itself. With a diameter of approximately 600 nanometers, the brochosomes are roughly half the size of a single bacterium, while the pores within the brochosomes measure around 200 nanometers. Wong raised an intriguing inquiry, prompting us to ponder the underlying reasons for such unwavering uniformity. What is the enigmatic secret behind the brochosomes, measuring approximately 600 nanometers and possessing pores of around 200 nanometers? Is there a specific function or purpose that these characteristics serve? In their study, the scientists discovered that brochosomes possess a distinctive structure that serves a twofold function. Firstly, it allows them to absorb ultraviolet UV light, thereby diminishing their visibility to UV-sensitive predators like birds and reptiles. Secondly, it enables them to scatter visible light, effectively forming a protective shield that reduces the risk of reflection and potential dangers. The precise dimensions of the apertures within the brochosomes make them ideally suited for absorbing UV light. According to researchers, the utilization of synthetic brochosomes in humans holds immense potential for a range of purposes. These include enhancing the efficiency of solar energy collection systems, developing coatings that shield pharmaceuticals from light-induced harm, creating advanced sunscreens for superior protection against sun damage, and even constructing cloaking devices. However, before any of these applications could be explored, the team faced the significant hurdle of producing synthetic brochosomes. By replicating certain characteristics of brochosomes, such as the arrangement of dimples, with synthetic materials in their 2017 research, the scientists were able to gain insight into the optical attributes of these tiny structures. However, their efforts only resulted in a resemblance to brochosomes rather than an exact duplicate. Wang explained that for the first time, the researchers successfully replicated the precise geometry of the natural brochosome by utilizing cutting-edge 3D printing technology to create scaled synthetic replicas of the brochosome structures. Using 3D printing technology, the scientists were able to create a larger version of the brochosomes, measuring 20,000 nanometers in size, which is approximately 1/5 of the diameter of a human hair. The team successfully recreated the exact shape, morphology, and pore arrangement of the brochosomes, resulting in faux brochosomes that were sufficiently big to be optically characterized. The researchers employed a micro-Fourier transform infrared (FTR) spectrometer to analyze the interaction between brochosomes and infrared light across various wavelengths, providing valuable insights into the manipulation of light by these structures. The researchers have outlined their future plans, which include enhancing the manufacturing process of synthetic brochosomes to match the scale of natural brochosomes. Additionally, they will investigate other potential uses for synthetic brochosomes, such as their application in information encryption. This involves incorporating brochosome-like structures into an encryption system that reveals data solely under specific light wavelengths. In his observations, Wang highlighted the significance of their research on brochosomes, showcasing the importance of adopting a biomimetic approach in scientific investigations, wherein researchers draw inspiration from nature. According to Wang, scientists have found great inspiration in nature when it comes to creating innovative materials. While their study has concentrated on a single species of insect, there is a vast array of remarkable insects that material scientists have yet to explore. These insects hold the potential to assist in solving a multitude of engineering challenges. It is important to recognize that these creatures are not simply pests. They serve as a wellspring of inspiration. In addition to Wang and Wang from Penn State, the team of researchers involved in this study includes Sheng Shen, a mechanical engineering professor, and Zhuo Li, a doctoral candidate in mechanical engineering, both from Carnegie Mellon University. Shen and Li played a significant role in conducting the simulations for this study. It is worth noting that Wang and Li made equal contributions to this research, resulting in the researchers filing a US provisional patent. The Office of Naval Research provided support for this research endeavor. To support our channel's growth and ensure broader awareness, kindly hit the like and subscribe buttons. This will help us reach more individuals and disseminate valuable information. Thank you in advance.